Hello, my name is Wesley Carter. I am one of the co-chairs. Del Merriman is sitting up here with me, and we welcome you again. I'm going to move to a handheld mic. Want to thank you again for coming. This is our Tuesday, or our second day of a 3-day schedule that we have. This is our 5th annual. There's only a couple things I needed to say today. We'll go through some of these slides. We have authors and everything. We are scoring those score sheets. If you have any from yesterday that you did not turn in, please turn them in to the back table there, because you are a critical part of who wins first, second, and third place. And that is a very big thing for the authors and for the presenters that are presenting what the authors have put together. They spend a lot of time, a lot of energy on this, and this is a big part of this conference. Okay, thank you, and we are going to get started. Our first presenter is Nathan Simmons. He's a technical sales engineer with Bruker Optics, specializing in process analytical techniques for real-time chemical and materials analysis. He supports industrial customers across the oil and gas, chemical, petrochemical, food, pulp, and paper, and the pharmaceutical markets, which when I read that, I said, okay, everything but aerospace, okay? With a primary focus on Raman, FTIR, FTNR spectroscopy for In-Situ and online process monitoring. Nathan works closely with operations, engineering, and analytical teams to translate complex process questions into robust it's early in the morning. His experience spans flexible feasibility studies, probe, and sampling design system integration. At the AT conference, he's going to bring a practical, field-driven perspective shaped by hands-on work in real production environments. Outside of work, Nathan enjoys spending time with his family, don't we all? Pets, and recharging by hiking. Oh, that's way too much work. And in engineering, and exploring the outdoors. I want to thank you, Nathan, for coming in, and I'm going to turn this over to him.
Hello? All right.
Nathan, don't be shy.
All right. I will not. Okay. Well, good morning, everyone, and thank you again for coming out after a night of frivolity and fun. So early in the morning. So my name is Nathan, if I'm in trouble. So we are going to be talking about essentially Raman spectroscopy today, and specifically in the categorization of wastewater management. So I felt like that was something that applies to everyone. And so we've got two things going for us this morning, I suppose, with insofar as it being early. I am a retro vintage Marine that actually got a chance to be a master training specialist at one point in time. So hopefully you walk away from this presentation with a lot of knowledge about Raman spectroscopy just in general, and specifically with wastewater management. And then, I guess second would be that I was born and raised in Southeast Texas. So I seriously doubt anyone is going to be leaving the auditorium today saying, wow, that guy talks way too fast. So with that in mind, I guess we get started. And so see here. All right. So, I mean, we're just going to go through this. I'm not going to read slides. I think that's probably not what you're here to see me do, but I will talk about each one and then show you some data. So the general flow is going to be that I'm going to show you a little bit about Raman spectroscopy as it is, as it was, and as it continues to be. And then we're going to apply basically how we do it a bit differently with Bruker spectroscopy products, insofar as our high throughput virtual slit, right, which allows us a great amount of sensitivity to do lower concentration of analytes. And then we're going to apply that basically to wastewater, right? And so these compounds that we're going to discuss in this presentation are oxyanions, urea, ammonium, so things that are generally pretty common in petrochemical processes, fertilizers, things of this nature, right? So we tried to pick things that were just kind of out there, but one thing to take away is that this is not an all-encompassing set of samples that we can measure. So we can measure pretty much anything that has a Raman effect, and we can do that pretty effectively. So what's in it for you, right? So wastewater, I think every manufacturing process in the world produces some manner of wastewater. And because the water is contaminated, you don't want to send that literally downstream. So we have a responsibility to clean that up. And understanding how those processes work and basically understanding what's coming and what's leaving is really critical, right? So, and because, you can basically avoid just a whole lot of trouble and fines and things of that nature. So, okay, so wastewater compounds by industry. Some of these industries are going to be, fairly familiar, but it's basically all industries have wastewater of some sort. So we can just move on from that one. So what is Raman spectroscopy? So it is essentially, in a very small nutshell, you're going to take a laser of some frequency and you are going to apply it to a sample medium. And inside that sample, you're going to have millions of little molecules, and they're going to do things with this laser. They're going to interact with it. And basically one out of every 1 million of those little molecules is going to release a photon of light that you can actually use. So much like we were when we were teenagers, this is a very low energy, right? High input, low energy output. So essentially, Tornado spectrometers, and Tornado is a company that Bruker bought a couple of years back. But they have a very unique way of gaining sensitivity along with the selectivity that is so commonplace in Raman products. And they do that by using a high throughput virtual slit. So basically they'll take, and instead of blocking 90% of the light with a mask slit to gain resolution, they will cut up the light that's coming off of a fiber, which is just a round circle of light. That's these return photons, 1 in a million, right? So you got to catch them all. It's kind of like Pokemon. So the idea is that we want as much energy efficiency with Raman as we can get. But the trade-off to that is oftentimes resolution, right? So the things that you can take away from Raman spectroscopy just in general, why would you want to do it? It is a highly selective technique. I don't know what did that. So you are going to produce a spectrum that actually has peaks. They're not all convoluted together. And you're going to be able to tell what is what. We can do very long fiber runs, right, with Raman, especially with this technique. Sample calibrations are less intensive than some other spectroscopic methods. Let me see, did I miss anything? And model stability, less maintenance, right? So overall cost of ownership is lower on systems like this. So we talked a minute, just about resolution and things like that. So what does that mean, right? So essentially you get a bunch of light back, right? And you know that you're not getting a lot. You're only getting 1 in a million photons is coming back up that pipe. So you got to do as much with the photons that you have, right? And that's where this segmentation goes through. So essentially, conventional spectrometers just have what they call a mask slit. So that is really just a piece of metal with a slit in it. And that allows only, a very small amount of these photons through, right? And you can see what that does to resolution. When we talk about this slit and the purpose of the slit, we really want to be able to resolve peaks because, as I said before, it's kind of one of those deals where, one of the main benefits of Raman spectroscopy is the selectivity, right? But sensitivity has always suffered as a result because that slit blocks so much of the light. So what we've done is we've rearranged the light into the shape of a slit, and now we get the best of both worlds. And that is what allows us to do things like wastewater management and really low ppm detection limits. So the way Raman was it was always great with selectivity, but it suffered in sensitivity. And now we have a new way. So we can take that through many of our spectrometers, right? We have 3 dispersive Raman spectrometers that we use, but we can put those into processes using chemometric modeling. We've got, I think, 4 different types of chemometric modeling softwares that we can use. Build you a model out of very few samples and get it going for you. So when you're talking about wastewater, what's useful? It'd be really nice to know what you have coming to your processing unit. This is almost any processing in chemicals, petrochemicals, oil and gas. If you know what's coming, then you can run your process equipment efficiently to deal with that. So wastewater is no different than that. So we have the incoming and we have the outgoing, arguably much more important, right? Before it goes literally downstream, you want to make sure that it's clean. That way, concerned citizens and government agencies and all those folks that are going to come after you do not come after you. Oh, I hit the wrong button. Very sorry. So we can go through the phosphate species. I'm not going to linger on these files a lot. These slides are basically for your reference. But again, they're not an all-encompassing list of analytes that we can go after. Definitely success with other things, polys and other little things that end up in your wastewater streams. So we are creating very discerned, separated, selective peaks of interest. And you can tell that as you kind of increase or decrease this, these compounds, that those peaks definitely change. And the area under those peaks change, and we build calibration models as a result of that. So this one here is from around 250 ppm to 1500, right? And then we have an R square, which I'm sure you folks already know all of this, but just in case, for those watching this presentation later, it's just how tight these predictions are following that prediction line, right? So you definitely don't want like an R square that's really low. Close to 1 is possible. So these are doing really well. And RMS ECV, this is error cross validation, plus or minus 50 ppm. So we can get very low with these. So yeah. So again, this one is 99, so almost 1. And we're talking about a error cross validation of 95. And what you're going to notice is that these measurement times, right? You might be confused. These are actually not typos. This is a very fast measurement technique. In most cases, it is extremely fast. The high throughput virtual slit allows you to do a couple of things. It increases sensitivity at the standard measurement times, right? So whatever you were doing before, if you do that, it will just increase your sensitivity by, I think, a factor of 3, right? So if you do it faster, you can still increase your sensitivity, but you can get these measurements very fast. So 2-second exposures, you know, again, R² of 95, error cross-validation of 203, right? So this is from 250 ppm to 3,000. Also important to note is just that these ppm levels, they were just what we had at the time. This is not some set in stone like level of accuracy that these things can go to. They can actually go lower than this. So nitrates, found in wastewater streams, definitely chemical processes all over the place produce these. And essentially, you take a nitrate spectrum and you can see that it's distinct from phosphate bands. Okay, and that is important because when you look at those, you can quantify them separately, right? So you can do these very critical attributes, multiple critical attributes across any sample stream. So you can look at multiple things same time. PLS models, 2-second exposures, R² 99, 0.99, and then we're talking about a error cross-validation on nitrates for 3.8. So very low, all the way down to 13 ppms. So tracking very well. This one went from 300 to 3,000. Again, very good R² and about 92 ppms of error. Sulfate and sulfites, more or less the same story. Very common in chemical processes. The band is distinguishable from other bands. But it does have some overlap that we can overcome with chemometrics. And by overcoming that, we can get an R² of about 0.98 and error cross-validation of 2.4 ppm, so very tight. This one was 250 ppm to 3,000. Again, great R² and 72 ppm of error. Petrochlorate, sometimes used in munitions. You might find it in other chemical processes as well. Chlorate and perchlorate, I might have mispronounced that before. Perchlorate, they're very similar. So we did our study with perchlorate. This has the lowest limit of all the detections that we have, right? And we're low order of detection, like less than 3 ppm. And we had this readily available to spike samples with, so we were able to do that very, very low. So PLS models, this was a longer measurement time, but it definitely gave us a good, like right side of the decimal point, good error cross-validation. Urea, I think we're all familiar with this product. Same deal, right? Very common. Gets in wastewater all the time. Has a very strong response to Raman and can easily be separated. The width of the peak does add some challenge to it, but we're able to overcome that with chemometrics. And 0.99 RMSE of 20 ppm. 2-second exposure times. Ammonium solutions, this is very common as well. Oil and gas, chemical, well separated from other analytes. So the specificity is there on all of these peaks. And where there is a little bit of convolution, we're able to overcome it and very quickly. So again, R² 0.99. And error cross-validation of 0.14, so all right, so DCM, acetonitrile, solvents that are commonly found, again, in wastewater streams, can easily be measured. You can see the separation there, and we're going from 0 to 200 ppm in these. So we're using 2-second exposure times, 45 averages, and we get a very good R-square and a very low error cross-validation. That's all the way down to 0, and this one was taken, let me see. Okay, so 10 ppm and 50, right? So these acetonitrile. This was a total measurement time of 2.5. Again, R-square, 0.98. Error cross-validation, 3.6. So the overarching story here is that we can go very low, we can go very fast, and we have very little issue with chemometrics. So the conclusions from that, there's just a wide variety of applications that you can use this with. This is not just a wastewater application, but we talked about wastewater today because it affects all of us in one way or another. That said, the speed and sensitivity of the systems that are out there on the market today are really bringing back a lot of interest in Raman technology. So it's good to give it a shot. We definitely have as much information as you want about current models that are out there, nitrogen compound models, and I'm open to any questions. I don't know how much time we have left, but should we have any, you're more than welcome to ask me or my application scientist any questions that you have, or you can stop by our booth and see us there. We can cover everything. Yes, sir.
How do you keep the probes clean based on the fact this is wastewater?
Okay, it's a very good question. So how do you keep the probes clean? So in some cases, we have many probes, right? Some of the probes are actually non-contact probes. So that's one solution if you have really, really easily fouled kind of areas. You go through a sapphire sight glass, and we have a process probe that'll look straight through that glass at multiple focal lengths, collimated beams, non-collimated beams, all sorts of stuff. So that's one approach. The other approach, if it's not too bad, would be to plumb in a bypass. So for quick probe removal. So you essentially put your probe in a process stream, right? So directly in the stream, and then you create just a bypass loop so that anytime you want to segregate that probe from the flow, right? Cohe is important. You just turn those valves, pull the probe, clean it, and place it back in. Does that answer the question? Okay, perfect. Yes, sir.
Most slides you had were like a single component in water. Most of us have probably more than one component in that water.
Yes, sir.
How much components can you measure? Because I think I saw some of the spectral data and the Raman shifts were quite close together. Mm-hmm. Did you have experience in doing multiple components in the water?
Absolutely, yes. So you're never going to get a wastewater stream with one thing in it, right? So yes, everybody knows that. But that is actually one of the great things about Raman is the selectivity. So they're often very separated, or enough so that the chemometric processes can deal with it. And you're talking about programs like PeakSact, Solo, Panorama, and Bruker's Quant 3. So yeah, there's ways to deal with it with the PLS. So you can do multiple critical component analysis in one spectral shot. Sometimes you have to do two models, and you have to do like a multi-evaluation method, but there's ways to deal with it. Yes, sir.
Okay. Do you have a lot of problems with water turbidity and small particles when you do this?
Well, so there are probe solutions that we use to kind of deal with that. So there are total solids in wastewater. So for that non-contact probe solution, we'd have to make sure that we get it basically as close to that measurement glass as possible. You don't want a whole bunch of crazy spectral fallout. But if you do an immersion probe, a wetted probe solution, we have focal lengths of 0, right? So basically it's only what touches the glass. And in that case, a lot of times total solids is not a real big issue.
Yeah,
Absolutely.
in refinery samples, we often see wastewater with heavy emulsions, and those emulsions can often arise with coke fines and unresolved coke fine in water. How does Raman behave under those conditions?
So with co-fines, I might actually have to defer to my application scientist for that one. I'm not really familiar with this terminology. Colin?
I'm assuming like co-fines you mean like carbon-based. Yeah, just like fine particles that are entrained within the emulsion and everything else. Yeah. So when it comes to, I guess, co-fines and emulsions, we're going to deal with that in the same solution. Is that we're going to you basically use a shorter focus when we're looking at what's coming right up against the material rather than having a focus that goes deeper into the stream, because the emulsion and the fines are both going to, I guess, if depending on the carbon material, if it's like carbon black or something that's very absorbent, that's going to decrease the intensity of all the light that's getting through. But fines in general, regardless, and solids in general, as well as emulsions, will disperse a lot of the light. So that's why we use a very short focus, so we're getting what's coming right up against the sapphire window, or regardless of whether we're looking at like going through a window or using a probe-based solution where we've got the sapphire that's deeper in the solution, we're looking right up against that. Because that way we're avoiding all that scattering and we're still getting all of the signal. And I think most of these measurements would have been done with a short focus probe. That's going to depend on the material of the fines. If the fines are highly fluorescent, like they're made of, I don't know, something that you would see from bitumen, like the long conjugated double bond, something that produces a lot of fluorescence, the fluorescence will get in the way. But if it's just solid particles, we'll measure them the same as we measure anything else. And where the bands show up in the spectra is just chemically determined. With a lot of the carbon bands, they would show up in similar regions from what we've seen on here, but again, we're going to see, especially if it's large molecules, you'll see multiple different bands, and that's kind of the joy of chemometrics, that while many of these compounds, there's one or two simple strong bands. If you have more complicated materials that have many bands, the PLS models are powerful. You can separate out many of these things, even if it produces a very complicated spectrum, which also gets to the questions about wastewater having fouling and many different materials in there. That's the power of the PLS methods, the power of having a lot of data.
That's actually a good point too. I mean, I hate to quote G.I. Joe, but you know, basically you never know until you try, right? So knowing is half the battle, and if you have samples or something like that, and you think Raman might be a good technique, the trying is not hard, right? So, I mean, we have the ability to take any of your samples that you can provide, and we've done this in the past, and just basically do a quick feasibility. That's what we're good at. So, so if you have some particular fines that are specific to your process and you're worried that they might fluoresce a lot, you know, there are ways to see if it's going to be a viable solution.
Any more questions?
Any others?
Well, my question is, can Raman technology be used for measure the heavy metal in the wastewater or in the mining tanning pump well measurement application?
Yeah, inorganics are kind of
Not
tough-
organic. Heavy
Like-
metal.
heavy metals.
Yeah.
I
Which
think that's
minimum amount, basically.
right. I think that's kind of a tough cookie to crack. I think we've had some success with minerals in the past, but I think it's kind of limited, right? So that would be a try it and see. I feel like kind of thing. So how low? Well, I mean, we can discuss it, but how low do you want to? What are your concentrations of these heavy metals, and what are they?
Okay. It's all depend on the application, what happened.
Exactly.
So do you have any recommendation for that measurement?
I think really heavy metals, that's kind of like an XRF thing, right? So, I mean, inorganics are just, it seems to always go to XRF. So,
Thanks.
Okay, if you have any other questions, can you please see him after his paper? We have to move on to the next one.
thank you, everyone. Appreciate it.
Our next presenter is Dakota. How do you spell? Morales. He is a PhD. Works for product. He's a product specialist for Ariba Instruments. Dakota is out of Utah. He specifically works and focuses on translating advanced analytical technologies into process tools for real-world processes. Dakota earned his PhD in chemistry from the University of Utah. I'll leave it to you.
Right, thank you.
You don't normally see that.
No. All right, good morning, everyone. Thank you so much to ATC for having me. This is my second year at ATC. So last year, I didn't get to present a technical paper, so this is my first time getting present at ATC. And over the last year or so, I've had the pleasure of getting to meet, our friends and clients in places like the Netherlands, people from Thailand that I met last year. Very unique places, Minnesota, so it's really nice to be able to come here and see all these people gathered here at ATC. So thank you for having us at ATC this year. So just a little bit more about me. I have my PhD focused in physical chemistry, specializing in spectroscopy in school, both in my undergrad and graduate schools. I studied organic and inorganic chemistries. I grew up in Western Pennsylvania, right on the border of Ohio and Pennsylvania, so right where the Shell ethylene cracker in Monaca is. So in my undergrad, when we would have chemistry speakers or engineers come to our seminars, it'd be people that are just like you that would come and present to our classes. So being able to be in this industry now professionally is sort of like a full circle thing for me personally. Like in the introduction, I'm a product specialist with Ariba Process Instruments. So Process Raman is my line of products that I focus on. Lots of sales, lots of technical stuff. I think all of my, people that I know in the audience here today, they see my eyes light up a little bit more when I get to talk about the science part of everything, I focus a lot internationally. In just the 2 years that I've been with Ariba, I've been able to expand in over 20 different countries and every continent on the world except for Antarctica. But one day I'll find something to do there. So yeah, there's a little bit more about Ariba. This is for sure going to be another Raman spectroscopy talk, and I know this is probably like at least the 6th or 7th one that you guys have seen at ATC so far, but something that I think that really separates, what we can do with, Raman spectroscopy comes from the fact that we've been doing this for over 30 years. So while Raman is on trend, this is equipment that we've been focusing on this entire time. So I live in Salt Lake at our factory for our process ramen with Hariba. So like I said, and as you guys know, this is definitely not the first ramen talk even today, even though I'm going second, let alone all the ones yesterday. So I'm sure all of you could be qualified to apply for, a PhD in ramen as well. So I'll keep this really short. But Raman spectroscopy is a light scattering technique, so it is not absorption-based. So a lot of the issues that come towards absorption-based spectroscopy, such as NIR, FT-NIR, Raman does not fall victim to those same things because it's just an entirely different physical phenomenon and reaction to light. And I think the main point that we really want to make here for Raman spectroscopy is the fact that every molecule in the world has its own unique spectral fingerprint in Raman, much like how every single person in this room right now has a different fingerprint than anyone else. So do molecules. And so how, forensics, can use fingerprints to solve crimes. We can use fingerprints of molecules in Raman to see, what components are, in your process, what components are adding to a property of your process. And this is where, Raman spectroscopy really, really shines, is this idea that these fingerprints can be resolved and quantified. So I'm going to talk to you guys today about acid gas loading in amine units. So this is something that we have seen time and time again when we visit our customers in the gas and oil industries and, specialty chemicals, that amine units are kind of like the black sheep of the plant, right? They've been around for forever, but it's really interesting in the fact that although it's a very established, sort of chemical process, not so much attention has been given to optimizing it over, the last, couple of decades. But Raman should be able to change the direction of that. So for those of us that are not too familiar with what we mean by acid gas loading, that is just very simply how much carbon dioxide and hydrogen sulfide are in the amine solvent at that exact moment. So it's just an indicator that's telling you like how much capacity is left in the lean amine before it returns to the absorber in the amine unit, the absorber's effective capture, capabilities, things like that. So it's just a quantitative measure, but why does it matter? From an operational standpoint, very high loading or very high amounts of acid gas in the lean amine reduces treating margin, which is a big problem. No one wants to lose money if they don't have to. And so unexpected shifts from rich amines to then the lean loading are one of the fastest way to pinpoint regeneration problems in amine units, which is faster troubleshooting, less downtime, so on and so forth. So I won't spend too much time on this. I know it's a little text heavy, but some common loading patterns and what they indicate from what our customers tell us when we go on site with them is when their lean amine loading is above baseline. And what the operator actually sees there is reduced solvent capacity, higher stream duty, or circulation required to hold that spec, which is just wasted energy and wasted money. Sometimes operationally, they'll see their rich amine loading increase abruptly, so it'll just spike out of nowhere. Their feed could get soured, and what an operator sees at that point, that lets them identify that that's a problem, is there's higher uptake in the amines, the operating changes need to happen to protect the treated gas quality. So again, just trying to get themselves back on spec. And then, when the treated gas goes off spec with no change in the rich amine loading, this is probably the biggest issue that we see from, the anecdotes that our customers share with us is strongly indicative of an absorption side performance limitation. So there's something actually wrong with the hardware in the amine plant. And so that just means that there's more circulation that has to happen, and they might, kick the stripper up, but there might be limited improvement in what they're actually stripping off of the amines. And so basically what we've seen is that you can't control what you can't see. So if you can't see these things in real time or know that they're happening, then how do you fix it? So traditionally, right, in today's world, most amine units don't actually directly measure loading online. Instead, they measure signals that correlate under limited conditions. So they are really looking at like bulk property signals like conductivities, densities of the rich and lean amines, refractive indexes with refractometers, treated gas analyzers, things like that. And each of them have, each of these are really good at the narrow sort of area that they measure. But they also come with cons, as all analyzers do, of course. But what if we could do something, that does all of this together instead of having individual, analyzers that aren't really even doing things online in a, unlimited way. So the most direct and traditional method that we've seen at these, amine plants is automatic wet chemistry. So these online titration analyzers, they can do lots of things like target the amine strength. So how much capacity does that amine solvent have left? Total acids, the pH of it, obviously, is a good one. And it's way more chemically grounded than bulk property measurements that we went over, like on the previous slide. And these actually can provide those periodic conditions of, the amine. But it's very sensitive to the sample. There's a ton of sample conditioning that has to happen before, you can bring it into an online titration analyzer. You have to temperature control it. You have to relieve pressure. These are very sensitive to how the sample meets the analyzer. Calibration upkeeps, there's lots of costly reagents and consumables. And cycle times can take tens of minutes, and that's not really online at that point, right? But the value of real-time acid gas loading measurements comes from the fact that real-time should show you what's happening, not what happened. So instead of being reactive, being proactive with that. So with traditional monitoring and very limited visibility, right, there's no direct acid gas measurement or just really slow ones. A lot of our customers run their regenerators with very conservative stripping severities. Because they don't know exactly what to do at that moment, so they just kind of run it just to make sure that they will for sure be on spec. And probably the biggest time consumer of all is the troubleshooting that comes from this when they have to take samples and do it offline in the lab. That's obviously time lagged and can be super sample dependent on that minute or whenever that sample is collected. But in real time, you should be able to have faster responses to feed souring and upsets, less default overstripping when you're just running the steam at a really high, energy level just in case, so you're not off spec. And just earlier warning signs of if your actual hardware is failing for your hydraulics and things like that. So I know a lot of people, if not everyone in this room, cares a lot about losing money in their process, right? So, and in acid gas loading, this is certainly a thought as well. So for steam management, right, most amine units will run overstripped to protect the margins on their specs. And the return of investment of being able to sort of tone that down really comes from reducing the steam rate. How much does your steam cost in terms of energy, utilities, things like that. Unused treating capacity. So basically what this means is, if you're kicking your rich amine out faster than it should, actually be removed or regenerated. You have better throughput. Again, you're avoiding energy cost for your amine unit. Corrosion and fouling on your actual hardware within the amine unit. Higher acid gas, they're corrosives, right? So this can push corrosion regimes where you might see an upset or damage the equipment. And so fewer corrosion-driven events and fouling-driven cleaning intervals to where you don't have to shut down or take it offline or, to clean or to fix something. And probably a really important one too that should not go unsaid is the actual labor burden of manual sampling on a traditional offline analyzer. It's sampling of hydrogen sulfide comprised and compromised liquids is very labor intensive for like safety reasons. I mean, you have to have an engineer or a chemist doing those tests. The actual handling of the sample needs to be done correctly, and that obviously takes time. So in a really, straightforward situation, we don't have to like boil the ocean, right, to get the information that we need in an application like this. We can just look at two places in a typical, amine unit, right? We can put a Raman probe, so a sampling point right at the beginning of the rich amine, and then put another Raman probe at the very end of the stripper where the lean amine should be coming out. And the lean amine to the absorber is basically just showing a direct readout of regeneration completeness. So did your amine do a good job with the stripper to get all that stuff out? The rich amine is, the direct readout of the absorption uptake. So did the amine do a good job of actually taking all of the acid gas in? But both, and monitoring both at the same time, enables really, really good monitoring and discrimination between when your regenerator is limiting your acid gas loading or when the absorber is limiting your operations. So another way to think about this is feed souring versus hydraulic degradation for these units, and being able to quantify these sort of things like acid strength, heat stabilized salts, which I'll get into in a second. All of these can be correlated to these operative signals that are important to engineers. So this is a nice Raman spectrum of monoethylamine, 30% in water. So you can see here that the matrix sample of this MEA, really the peaks that we've been looking at in this study really basically go from about 700 wave numbers on the bottom down to 1700 wave numbers, so just in a 1,000 wave number range. For our purposes and the way that we want to build the chemometric models for our Raman spectroscopy, we don't need to look at anything past 3,000 wave numbers, so those big bands for the CH turns and things like that, we can focus on just this fingerprint region at way lower wave number energies, and this is just more than enough to get the job done here. So mixtures of different amines and CO2 loading all have very distinct and unique Raman peaks, right? Just like I said at the beginning, everyone in here has their own fingerprint, well, so do these amines. So here's some spectra showing different concentrations of MEA, MDEEA, CO2 loadings in them, so on and so forth. And all of these amines give really clear and really nice, sharp Raman signals that is very easily to correlate, from component percentages of, what this amine is versus what that amine is. Even when they do share and overlap peaks, there are still enough uniqueness, I guess is a good way to think about it, from solvent to solvent when we are, correlating these things in a model, for example. So a really important point, that a lot of our customers talk to us about is this idea of heat-stabilized salt monitoring. So heat-stabilized salts are just anionic species that do not regenerate in the stripper. So once they are formed, they remain in that amine solvent loop for forever until that amine gets taken out and then the new one gets brought in. And so over here on the right side of the slide, are different fingerprints of Raman signals of very common heat-stabilized salts, such as oxalates, cyanates, thiocyanates, sulfates, all of those problematic salts here. And, by being able to directly measure these heat-stabilized salts down to double-digit, single-digit ppm levels, is that this is helping extend the solvent life, minimize steam usage from optimized lean loads. So instead of just running your stripper and your steam over and over and over again, your solvent might already be done because of these heat-stabilized salts being too high anyways. So we did this first in a very controlled setting in our R&D laboratory in Salt Lake City. So we measured up some MEA samples, dissolved from CO2, some sulfide in there to get our acid gas loaded into our MEA, and then spiked the samples with several different high and low concentrations of the common heat-stabilized salts that we've learned from our customers. And someone made a really good point yesterday that when you see these R-squared values in these modeling results for something like spectroscopy, right, they are not these like 0.9999, residuals that you see in things like GCs or mass specs and things like that. Really the way to view the capability of a model and the accuracy and error of it is to look at the root mean standard error of the model result. So it's also really important to remember that the error is always correlated to the range, right, from the min and the max there. So being able to, get down to double-digit ppm accuracy, 2 orders of magnitude less than the maximums here, is the exact sort of accuracies that our customers explain to us that they're looking for these sort of concentrations and samples in these, for these heat-stabilized salts. So really good results. We were very happy with this in the laboratory, but that's what happens in the laboratory is definitely not what happens online or in a process, as everyone in this room knows. So we had to take this out into the field, and we worked with a customer to do some more real sampling of their amine solvents. And so they gave us all of these different parameters, and we were able to correlate things like the formates, chlorides, sulfates, the MEAs, DEAs, MDEAs, the free amines, the bound amines versus the free amines is a big one for this customer. So being able to build these models and sample these in a real life situation was really powerful to be able to validate what we were seeing in our laboratory results as well. And then likewise, another stream that we were working with, looking at something like DGA, so a little bit of a deviation from the MEA or MDEA strategies that an amine unit might use for acid gas loading. Being able to look at properties like total alkalinity, looking at things like lactate, direct measurements of nitrogen content, things like that were all really powerful for this demo with our customer here. And I should also note too that for these results, these are 50, 60, 70, 30 samples in total that we were able to collect with this customer over a few days and prove the concept. So just to wrap this up here now, all of our spectra for all of these demos were done with our Hariba process Raman benchtop analyzer, and all of our chemetric models were built with Eigenvector Solo. So thank you to the folks at Eigenvector for providing the software with us. And yeah, just to end it here, I think it's clear that we can do a direct Raman measurement of our acid gas loading of your acid gas loading process. The model accuracies that we got were all within ranges that our customers are looking for in terms of accuracy, measurement times, the things that actually matter in real life for saving our customers money and providing them an ROI that they can get quickly. And yeah, these results, I believe, substantiate the feasibility of implementing these of our process Raman platforms in a variety of different amine unit sort of applications. And yeah, that's about it for me. So thank you guys. Yeah. And if there are any questions, I'll be very happy to answer them.
And my first question is, how long is that maximum length of your fiber optical cable? Because I noticed you have that one connect to the control room. My understanding is your Raman analyzer is not classified and cannot be installed in the classified location, right?
So for our Raman analyzers, we can put them in a purged enclosure, and we can put them into Class 1 Div 1 and Class 1 Div 2, or Zone 1 or Zone 2 ATEX areas. We can also sample. We can put our sampling points within Zone 0 ATEX hazardous locations as well. But if the customer does not want to put it in a purged enclosure and just wants it in a general like safety, just a general purpose room with other analyzers. Our maximum fiber optic cable length is 350 meters from that analyzer.
350 meter, okay.
Yeah, so you can put, so if there was, essentially 700 meters of length between, those 2 points, which would be extremely long for an Amine unit, you could just put the analyzer somewhere in between there and, sort of octopus arm it out to each of them.
Okay, thank you.
Yeah.
My second question is, so normally when you deal with your customer, so when you installed the analyzer, how long will it take, normally average, for you to working with them based on the field lab testing? How long will you need to build up a reliable model?
Yeah, that's a really great question. I think it just depends on the process. The way that I think most Raman companies do it, I know for sure this is our strategy, is we'll start building the models for an online process even before the analyzer is brought to that site to be installed. So we'll bring, or we'll have them give us samples like from their online process, and we'll run it on our instruments, help build the model beforehand, transfer it onto their analyzer so that when we do the commissioning or the installation of it, we can immediately start getting results. And they might not be exactly perfect, but from the combination of things that we did beforehand, the commissioning, to when we can start collecting samples within the first day or two after the installation or commissioning, the sort of like conglomeration of both of those, gives us the ability to start getting those accurate results within just days of the commissioning. So I think that's probably the strategy that we've seen works the best. Yeah.
Thank you.
Yeah, thank you. Yes, hello.
Hi, Dakota. This is Martin van der Veer.
Hi, Martin.
Did you try to model the rich A mines already? Because if you get higher concentrations of H2S and CO2, I can see some safety issues and some flashing in those things.
Yes, for sure. So that's a really great question. So yes, when these results back here, yes, so these are definitely from the combination of modeling off of the lean and the rich amine. So yeah, you're exactly right. When you have a bunch of, that acid gas, especially the hydrogen sulfide, is way more problematic than the carbon dioxide, right? Saturating or dissolved into those samples, it requires very careful sampling. And so I think this was something that was really good to learn of, that's why I made that point in the slide earlier of the labor burdens of these liquids that do get, compromised by these high acid gases. When our customers have to, sample or run the risk of flashing that, or, the toxicity of it, every single day that they're sampling that, versus them just doing that with us, and then we can put this online to model that with the model, really should transform that labor burden. So where that exact question that you asked, maybe they only have to do it once a week or once every couple of weeks or whatever, whenever they need to do for their own reference methods. So, but yeah, it was a really unique experience getting to work with these very high-level hydrogen sulfide gases. It made me feel like I was back in, the lab for sure. Yeah, it's a great question.
Thank you, Ryan.
Yeah.
Or thank you.
Yeah, no, thank you. Okay.
Ryan's my next guest, so sorry.
Good luck. Yeah, no.
Our next guest is Ryan Leroux. I'll let him pronounce his last name. Ryan is a product manager for Process Insights. He specializes in optical absorbent spectroscopy. I said it this time, didn't I? Including FTIR, NIR, and UV-Vis. He has a PhD in applied physics from Portland State University. His doctorate dissertation was titled Sensors and Portable Instruments for Post-Harvest Agriculture. He's contributing to a chapter titled Considerations when Selecting Sample Interface.
Awesome, thank you so much. Perfect. Okay. Thank you. So my talk's a little bit different. I'm going to talk about things that are pretty much common sense, but we seem to always mess up as an industry. So this is all about critical considerations for all the different kinds of probes, whether it's a UV, whether it's an NIR. Some of the same stuff applies to like Raman probes when you have in-situ measurements. Where's the clicker? This? Okay, so what is the sample interface? The sample interface is usually that probe that we have either in a bypass line or directly in situ that's sitting there, and that's where the light and the sample are interacting. And it really doesn't matter how good of an analyzer you buy. If that probe or that sample conditioning system fails, if it plugs up, if it fouls, your analyzer's no good, right? If somebody comes through and they drive a forklift through your fiber cable conduit and they break the connection, that $1 million analyzer or that $30,000 analyzer isn't gonna give you any information. You're gonna be running blind, you're gonna be back to grabbing samples. So what this talk is really about is all the careful consideration that needs to happen when you're going through the proposal piece, whether you're a process engineer, whether you're a tech that's looking at doing some maintenance, or whether you're like a system integrator trying to pull together all these pieces from different vendors. One of the easiest ones to keep in mind is material compatibility, right? Code of construction requirements. If you're doing an acid, you probably don't want a 316 material. You might want something like a Teflon flow cell, right? Because the Teflon's gonna handle those acid conditions. Maybe you want a C276 Hastellate probe. Everybody gets this. We usually don't mess this one up. But some questions to consider are like, what are the occupational health and safety risks if those seals fail, right? Does a probe have a secondary seal so if we do get a leak somewhere because we messed up and we picked the wrong O-rings, we put Viton O-rings in and we should have had Calres 7075 O-rings, what happens? What grade of O-rings do we need to have? Can I get away with a metal braze to seal the glass optics to the rest of the probe? Do I need the O-ring seal? Do I need something else? So these are some very basic, simple questions to make sure you're setting your specifications correctly. The next one, we also think it's pretty simple, is a temperature and a pressure, right? All these probes have some kind of temperature rating, they have some kind of pressure rating. So that should be really easy to line up, right? Because you know how hot your process is. Well, will the probe act as a heat sink? If you're a polymer plant and you got this stainless steel probe sitting there, is that gonna cause fouling? Is that gonna mess up all of your process because your heat is just gonna go right up to that probe and it's gonna radiate out? Can a probe handle thermal cycling? If you're in a reactor and you're doing a wash at the end and you're putting 80 degree xylene into a 230 degree polyurethane reactor as a wash, is that thermal shock gonna kill the probe? So some of these kinds of maintenance, serviceability, lifetime things are often overlooked. One of my favorite ones, I recently just had to deal with this in a semiconductor application, had to do with material of expansion. So they had a process that needed a different grade of metal. And we said, okay, well, we can take that grade of metal, we can put it into this kind of a probe. Well, everybody just kind of assumed the CE was gonna match up, and it turns out it didn't. So we had to heat the probe up really, really slowly when they were bringing it up. Otherwise, we were gonna crack the optics. That was a painful mistake for everybody involved. Here's an example of a probe that was brought to above its design pressure. Might be a little bit hard to see, but that should be a 316 Schedule 40 pipe sticking out of that flange. It's crushed. So there's actually fiber cables in there. What was interesting about this is this probe was actually still useful. It didn't break the probe itself, it just crushed the pipe. But somebody missed a specification. Here's a process event. Somebody said, oh, my process doesn't get very, very hot. Well, they didn't think about the thermal soak and everything else that's gonna be happening, and they burned up the probe, right? The stainless steel there got blued. We actually debrazed the optical window, the metal seal there on the bottom in this big left photo. I don't know where the window went. It went clinkety clink clink down. It's probably in somebody's valve. So making sure that the temperature specifications that you're actually going to get are going to work. Did you wrap everything in heat tape? You set the heat tape to 60 degrees, but all that sits there and it just cooks, and you don't actually have temperature control over where your process point's at. These are expensive mistakes. Another thing to consider is your leak rate and your fluid density, right? We all know balloons, we can fill them up with helium, and that helium slowly escapes. Everything leaks. So you need to know how much of a leak rate is acceptable for your application. And what does the vendor do for testing the leak rate? And how does that leak rate test compare to your process? So if you say, hey, I'm running at 200 degrees and I'm running at 500 pounds. I want to do a 2000 PSI hydro test on the probe to make sure that it's safe. Well, I don't know anybody that's going to do a 200 degree hydro test, right? So we're going to do a room temperature hydro test. So what kind of derating or verification do you need to know that as you heat that up, it's still going to work, it's still going to hold as a seal? Do you need to have something that's actually virus tight, even though you need something that's technically watertight to handle that derating due to the pressure changes? The next one is flow conditions. So inside, if it's an insertion probe, you usually have some kind of notch like this. And it's got to flow through the notch, and we actually make the measurement when we do optical spectroscopy through the little two windows there. How do you know that you're getting good, steady state flow, whether it's laminar or whether it's turbulent, and not in this interstitial region in between where you can get bubbles and other things that are going to throw off the reading? Well, we sat down and we did a COMSOL study. We took that notch and we just sat there and we kept rotating it. And we actually found that a 5 degree notch gives a little bit more of a shoot through, a little bit of a pressure effect to help actually clean the windows. And it actually speeds it up faster than a 45 degree. And if you had it at a 0 degree, you have that leading edge. You get all kinds of weird flow dynamics. You get cavitation, you get buildup. Well, that to me sounds like fouling. Fouling on the probe isn't good, right? Because then you're going to have to increase your service maintenance. So just something as simple as how did we clock this probe into the process can make the difference between your $50,000 analyzer working or not working. Here's an example where we did everything right. We put it together. It gets handed off to the construction crew, and there's no serviceability here. They installed the probe into the pipe, and then they welded the pipe up underneath an I-beam. That should be a probe that gets extracted out. That's an extractor assembly. There's not enough vertical clearance between the top of the probe and the bottom of the I-beam. That probe's never coming out. That means you can't clean it if it fouls. You can't take it out and re-zero when you change out the light bulb. I don't know what to do in that situation. That's a really expensive rework, right? Because then you got to wait for your turnaround. You got to cut this pipe out and you got to turn it around. You guys know how often there's turnarounds. That analyzer ain't doing anything, right? For what, 6 months, a year? Here's another example. Somebody actually put this flow cell into a box because they wanted it protected because it's sitting outside. Well, there's supposed to be this cleanout port. That's what the hex head is here on the top right. The hex head's facing the back of the box, back of the box. So you guys tell me, how are you going to take it out and clean it? Now again, you got to wait for your shutdown. You got to take it all apart, disassemble it, go back in. You can see they potted this in with some goop. It's a big pain in the ass. All because somebody didn't pay attention, walk through the construction, make sure that we're following the directions, everything that the process engineer or the system integrator may have talked about didn't translate down to the end. Somebody didn't read the paperwork. So in summary, it's important to make sure that all this stuff lines up, that it works, because the most expensive analyzer in the world isn't going to be successful if the sample conditioning and the probe isn't fit for purpose, if it's not designed to meet the requirements. You guys have any questions?
I don't have a lot of experience with these optical probes, but I do recall occasionally seeing situations where they may have type of a cleaning solution or even a mechanical scrubber. Any insights? One, does that still happen very much? And if so, any insights of how that could be done more correctly than not?
So there's different ways that they can handle that, right? Some people might do like a steam flush, right? What I don't recommend is anybody take a steel brush to the probe. That happens more often than I care to admit, right? And it comes back, it's all scratched up, it's fouled. They nick that seal, probe fills up with process, it's no good. Typically, you're gonna pull it out, you're gonna clean it up with some cotton swabs, whatever solvent is gonna take away whatever might be building up on the windows. But it's really a function of how clean or dirty your process is, right? If you're using a probe for like gasoline blending, that probe's always clean, right? Because it's just sitting in nice solvent. You're in a nylon 666 plant, that probe's fouling up every couple of minutes. So you gotta have a nice, repeatable serviceability.
Any other questions?
I would say it's not only for optical probes, it's for all sample systems, for all sample handling, and especially sample takeoffs. We see too many dangerous events happening with sample probes. It's a very high risk thing.
No, a lot of the same rules that we have for putting in like a flow meter apply to all these optical probes, right? Because you need fully wetted flow to get a representative sample, and it needs to be nice and consistent.
Yeah, I would say be very careful, especially with optical probes as well. They typically don't meet piping specifications, so you would have very special procedures with your mechanical department and piping.
If you take steel wool to your optical probe, I want to be the probe manufacturer. Any other questions?
Cool.
Thank you, sir. Thank you. Good job. Okay, you're released now to go downstairs and go through the gauntlet. And our break is downstairs. Thank you.